Have you ever just looked up at the sky and wondered, how? How does something that weighs hundreds of tons just float up there? It really feels like it should be magic, but it's actually physics. And today, we're going to pull back the curtain on the incredible invisible force that makes it all possible. Let's get right into it.
I mean, really, stop and think about that for a second. We're talking about a gigantic metal tube, heavier than a blue whale, just hanging out in the air. It seems to defy gravity, it defies all common sense. But the answer to this massive mystery, it's surprisingly simple. In fact, we can pretty much boil down the entire secret of flight, and a whole lot more, to just a single, powerful idea.
And that's it. No, seriously, that's the entire secret, right there. Fast-moving air means low pressure, slow-moving air means high pressure. This one simple rule, discovered by Daniel Bernoulli hundreds of years ago, explains so much about the world around us.
So, the really crucial thing to get is this inverse relationship. When one goes up, the other has to come down. You can kind of think of speed and pressure like two kids on a seesaw. If speed is way up in the air, pressure has to be down on the ground, and vice versa. They can never, ever both be high at the same time.
Now that might still feel a little abstract, I get it. So let's make it way more concrete with what is probably my favorite analogy for this whole thing. Forget about invisible air molecules for a second, and let's picture something we've all seen, a super busy school hallway.
Okay, so picture the wide part of the hallway. The students, those are our air molecules, they're just strolling along, They have plenty of time to spread out, lean on the lockers, bump into the walls. All that pushing and bumping on the sides, well, that's like high pressure. But then, everybody gets to a narrow doorway. And what happens? They have to speed up. They have to rush to get through. They are so focused on just moving forward that they stop bumping into the sides. And that's our low pressure. Air does the exact same thing.
So why does this trade-off even happen? Well, it all comes down to a really simple budget.
Yeah, just like you have a budget for your money, the air around us has an energy budget, and it can spend its total energy in two main ways. Either by pushing outwards on stuff, we call that pressure energy, or by moving forwards, which is its movement energy, or its speed.
And this just perfectly illustrates that trade-off. If the air spends a ton of its energy budget on moving at high speed, it just doesn't have much energy left over to push on its surroundings, so you get low pressure. But if it's moving slowly, well, it's got a huge amount of energy left in the bank to push on things, and that creates high pressure. It simply can't have both.
Okay, so we've got the rule and we've got the why. Now for the really fun part. Once you understand this principle, you start seeing it absolutely everywhere. Let's look at some real-world examples. All right, let's go back to our airplane. Take a look at the shape of a wing. It's curved on the top and it's flatter on the bottom. As that plane moves forward, the air splits. The air that goes over that longer, curved top path has to travel farther in the same amount of time, so it has to speed up. The air on the flat bottom has a shorter path, so it can be slower. And now we just apply our rule. Fast air on top means low pressure. Slower air below means high pressure. And that high pressure air underneath the wing simply pushes the plane up into the sky. That pressure difference, that's what we call lift. Okay, here is one I know you've experienced. You're taking a nice hot shower, minding your own business, and all of a sudden, the shower curtain billows inwards and sticks to you. It's super annoying, but it's also perfect physics in action. So the hot water and the steam, they get the air moving really quickly inside the shower. And according to our rule, that fast-moving air creates a little zone of low pressure. Meanwhile, the calm, slow-moving air out in your bathroom is at a higher pressure, and nature absolutely hates this imbalance, so the high-pressure air outside pushes the curtain inward, trying to fill that low-pressure zone. You can actually prove this to yourself, like right now. Go grab two pieces of paper, hold them vertically, about an inch apart, and then blow a fast stream of air right between them. Now, you'd probably expect them to fly apart, right? But they do the exact opposite. They snap together. So why? You created a channel of fast-moving, low-pressure air, and the calmer, higher-pressure air on the outside just pushed them right in. You just demonstrated Bernoulli's principle with your own breath. Now let's scale this up to something way more powerful. When a tornado or a hurricane hits, roofs can be literally torn from houses. And while the wind itself is destructive, it's often a massive pressure difference that does the real, shocking damage.
See, the incredibly fast wind speeding over the top of a roof creates this extreme zone of low pressure above it, but the air inside the house is still, it's at normal high pressure. Well, that high-pressure air inside has nowhere to go but up, and it pushes on the ceiling with immense force. If that force is strong enough, it can literally blow the roof off from the inside out.
So, we've seen this principle lift planes, attack us in the shower, and even destroy homes. It all just comes back to that one single, simple idea.
I really love this way of thinking about it. It's just a hallway analogy in a nutshell. Fast air is too busy going somewhere to push on things, but slow air is just hanging around, so it pushes on everything it possibly can. And really, that's the bottom line. It doesn't matter if it's air, water, or any other fluid, there is this constant, universal push from areas of high pressure toward areas of low pressure. This fundamental drive is what creates lift, it's what creates wind, and it's what creates so many other forces that are shaping our world at every moment. So, the next time you see a curveball swerve in a baseball game, or a flag flapping in the wind, or even just a piece of paper that seems to lift off a table, you'll know the secret. It's not magic. It's just a constant dance between speed and pressure. And now that you know the rule, I guarantee you're going to start seeing it everywhere.